Candice and Moraga, and I'm here today with you in my brand new diabolical laboratory here to do a lab on buffers. And basically, I started off by doing a million computations on buffers here so that I have a firm understanding of what I'm doing. Now, I haven't opened any crazy chemicals yet, but I've set everything up here so that I have a little 24 well plate here. I've got a couple of solutions, haven't opened them yet. The hydrochloric acid of a 6 molarity solution, aqueous solution here. And in this other pipette, I have sodium hydroxide, also a 6 molarity solution. Now, the hydrochloric acid you might recognize from being stomach acid. That is a very strong acid. And the sodium hydroxide is a very strong base. What I'm going to be doing is adding them to different buffers in order to see what kind of changes in pH I end up with. Now, our buffer solution is supposed to resist changes in pH by containing both a weak acid and its conjugate base. In this situation, I'm going to be using some white household vinegar, which is approximately 5% acetic acid. Now, the conjugate base of the acetic acid is acetate. So in order to make that, I'm going to have to first manufacture it to make a buffer solution. And I'm going to do that by adding 2 milliliters of the vinegar with 6 drops of the sodium hydroxide. And what that will do is cause a reaction that will result in acetate, sodium ions, and water. Basically, our buffer solution, the acetate being the conjugate base, the acetic acid, and there is the weak acid, and then you're just left with the salt water. Salt water in and of itself is not a buffer solution. You need to have a weak acid and its conjugate base. Then, after I've made that, I'm going to make 4 different wells with that. In 2 of the wells, I'm going to be adding our hydrochloric acid, and in 2 of the wells, I'm going to be adding sodium hydroxide. Now, in 1 of the wells, which I'll be adding the hydrochloric acid to, I'm going to add a super concentrated hydrochloric acid with a molarity of 6. In the other, I'm going to add a diluted solution of it. And I'm going to dilute it down by making it 2 milliliters water and 1 drop of this 6 molarity super concentrated acid. And that should bring us to approximately 0.1 molarity. So big difference in the concentration there. I'm going to make a diluted solution of the sodium hydroxide also by doing the same method. 2 milliliters of water with 1 droplet of the super concentrated sodium hydroxide to make a 0.1 molarity solution. So first I'm going to add the diluted amounts to our buffers of each of the acid and the base, and then I'm going to add the concentrated amounts to our acid and base. I also marked up some separate pipettes here with hydrochloric acid and sodium hydroxide, so I can reduce my percent error on this experiment. In the guide they suggested that I go crazy rinsing these out, blah blah blah, and I just thought, okay, that is crazy. So I have all these extra pipettes. I put some water already in this little beaker so I can measure from there using this little dropper, and I'm going to measure out the water first so that I don't cross-contaminate with the acetic acid, because I already know how this is going to go. I've got a couple, I mean, I can predict with my wonderfully expertise, expert knowledge in chemistry here. And I've got, I'm going to make 2 wells of just water, 2 milliliters water. And I'm going to add 5 drops of dilute hydrochloric acid to 1 well, and then 5 drops of dilute sodium hydroxide to the other well of water. And this is to ascertain how well the buffer waters. Now I already know that water is a terrible buffer. In fact, if you even like get a little bit of your breath onto water from like a straw or something, it's going to change the pH right away. So that's why we're just using the dilute amount. We're only doing 5 drops. I'm also predicting, as far as my results go, that I'm going to add 16 drops of the dilute acid and the dilute base to the 2 wells, because it's going to take longer for the pH to change, and then just 5 drops of the concentrated ones to it, because it's not going to take so many drops for it to change. Now I've already cut up all these different test strips of pH test strips, and the pH range I can measure using this little strip here, red, orange, yellow, light green, dark green, and a blue. If it's red, it's going to be more acidic, and if it goes towards the blue, then it's going to be more basic. So I can approximate the pH. Now, as I add the acid, obviously it should go more towards the red on the strips, because it will be getting more acidic, and it should take longer for the dilute ones to go towards the red. And I made up some handy little charts here for all of my observations. I'm going to record the approximate pH and the paper color of every single drop that I add. The lighting here is not that great. It's probably going to be hard. From my experience, it is hard to show you guys results on these videos. I'm so sorry. But maybe when I have some pretty looking papers, I'll be able to show you that. My videos tend to be sort of long anyways. But that's what I'm up to here. And I can already predict how my results are going to go. I mean, maybe not the exact color of the paper on what particular drop, but my hypothesis is that I should be able to predict whether the test strips are going to end up going more acidic or basic, and relative rates depending upon what kind of molarity concentrated solution I use. And also with the water, I can predict that it's going to change really rapidly. Practical applications of buffers include your blood has a weak acid, carbonic acid, and its conjugate base in there, so that you can regulate your blood to be within a specific pH range, so that you don't die, because your blood's supposed to be a little bit basic. So you want to keep the carbon dioxide amount stable, whether it gets too acid or too basic. Muy malo. So, okay, I'm going to get to work here. And you probably don't want to watch the whole thing because it's going to be a little bit time consuming, but I'll try and show you some awesome results. Peace out. Hello, I'm back to show you some of my awesome results and explain to you what occurred here. Now I've got open chemicals, so goggles are very important. This is the aftermath here we see with all of my litmus papers and everything. I had some different incidents with Will, so I moved to the second well there. I had the acids on the left side, and on the right side I had the bases. So you can see even the different solutions turn colors from these litmus papers that I went crazy with. My results definitely went along with what I said as far as the light here. As far as water is a terrible buffer solution. Buffers do work. At first I was almost wondering if I did this right, because nothing was changing. I was doing drop after drop after drop and the pH wasn't changing. So we know that these buffer solutions definitely work. As we viewed that I didn't mess up the solutions, it was still changing colors, just not with the buffer solutions. However, if you do it concentrating enough, even with a buffer solution, it will change. Provide some protection against change, but not complete protection. So what does this tell us?
as far as with your blood, for example, my prior example there, you do, since it has a buffer system, you do have some protection against pH change. However, don't think you're completely protected because, as we can see, it can still change in terms of pH. So try to maintain a healthy diet, do some deep breathing, and I'll be back with another diabolical laboratory experiment. Peace out!